Good afternoon, everyone, and welcome to Princeton University. My name is Dan Day. I'm the Assistant Vice President for Communications here at the university, and we welcome you to today's celebration of a Nobel Prize in Physics won by Professor Duncan Haldane. And we are delighted to have you here with us today, and also delighted to have those of you watching our live stream through the university website, and I believe also on Facebook. Before we begin our program, I'd like to give a few instructions on how this news conference and celebration will work. We will start with remarks by the president of Princeton University, Chris Eisgruber, and the chair of the physics department, Lyman Paige. After that, Professor Haldane will speak. When he concludes, we will open the floor to questions from the news media. I will call upon each member of the media, and we'll have a mic runner bring a microphone to the reporter so everyone can hear. We're also receiving questions remotely from the media, from those who cannot be here, and I may relay a few of those questions to the professor. Beyond the media, we have a good number of faculty, students, and staff here in the auditorium. Depending on the number of questions from the media, we hope and expect to leave time for your questions as well. And now, I'm pleased to introduce the 20th president of Princeton University and a former physics major at this university, Christopher Eisgruber. Chris?
Thank you, Dan. Thank you. It's my pleasure to be able to welcome all of you to this press conference this afternoon. Joining me here on stage are the chair of the physics department, Professor Lyman Paige, and of course the man of the hour, the 2016 Nobel laureate in physics, Professor Duncan Haldane. Professor Haldane's biography is now known to the world, so I will recite the details only briefly so that we can spend as much time as possible hearing from him. Duncan Haldane is the Eugene Higgins Professor of Physics at Princeton University, where he has been a member of our faculty since 1990. Born in London, Duncan studied physics at the University of Cambridge, where he received his BA with first-class honors in 1973 and his doctorate in 1978, but he told me as we were waiting just before this conference that he spent the last 2 years of those doctoral studies here at Princeton with his advisor, Philip Anderson, himself a laureate, who is with us here in the audience today. From 1977 to 1981, he was a physicist at the Institut Laue-Langevin in Grenoble, France. He then became an assistant professor at the University of Southern California in 1981, where he remained on the faculty until 1987. Duncan also served as a member of the technical staff at ATT Bell Laboratories in Murray Hill from 1985 to 1988, and during that time, luckily for us, once again, spent some time at Princeton as well. Following a stint as professor at the University of California, San Diego, Duncan joined the faculty at Princeton, where he has been ever since. Duncan specializes in the field known as condensed matter physics. His research has focused on the use of advanced mathematical methods to study unusual states of matter, such as superconductors, superfluids, or thin magnetic films. Despite the fact that, as Dan accurately said, I do have an undergraduate degree from this distinguished Department of Physics, I am utterly unqualified to explain Professor Haldane's work. I am going to leave that to him. But I will remind you all of what was said in this morning's press release. Along with David J. Toulis of the University of Washington in Seattle and J. Michael Kosterlitz of Brown University, co-winners of this year's Nobel Prize in Physics, Duncan has used topological concepts to explain the properties of chains of small magnets found in some materials. His work has important implications for the understanding of new types of materials with the potential to influence future generations of electronics, superconductors, and quantum computers. Duncan has been widely recognized for his path-breaking discoveries in condensed matter physics. He held an Alfred P. Sloan Foundation Fellowship from 1984 to 88 and was awarded the Oliver E. Buckley Condensed Matter Physics Prize from the American Physical Society in 1993. He is a fellow of the American Academy of Arts and Sciences, the American Association for the Advancement of Science, the Royal Society of London, and the Institute of Physics in the United Kingdom. He was also named by the Institute for Scientific Information in 2004 as one of the 230 most highly cited authors in physics. As I said, I will let Professor Haldane tell us more about the scientific details of his work, but I did want to conclude by adding a personal reflection. As a former student of physics myself at Princeton, one of my strongest memories of my undergraduate years here was the day in 1980 when Val Fitch won the Nobel Prize in physics. It was a wonderful moment for the department and for the university, a celebration of the truly groundbreaking work that goes on here. And as an undergraduate, I felt privileged simply to have a chance to watch the excitement from the sidelines. When I was up late at night, struggling through difficult problem sets in Fine Library, I would occasionally seek inspiration by walking through the halls of the physics building and gazing at the portraits of the many Nobel laureates who had studied in the department or served on its faculty. I am delighted today to see this marvelous tradition extended as Professor Duncan Haldane becomes the newest addition to this extraordinary department's Hall of Fame. Let me now ask Professor Paige to say a few words.
I was going to clap for you. You should clap.
Let me now ask Professor Paige to say a few words, and then we'll hear from this year's laureate.
Thank you. I'll be brief. Look, this is a very special award for us in a department of unusually creative people. Duncan stands out in the broader theoretical community of physicists. He is known for his extraordinarily deep insights. These are quotes from letters I've gotten over the years, and mathematical elegance. In personality, you'll see Duncan is lighthearted and funny. He laughs a lot. He has an ironic sense of humor he sometimes shares at faculty meetings. He tries hard to feign administrative incompetence. But in the end, he always comes through to help and support his colleagues and friends. He's an absolutely wonderful colleague. Duncan is a reminder of the importance of environments and communities like Princeton, where the pursuit of knowledge at the forefront of science can flourish. His exotic ideas came from this purely intellectual pursuit going back some 30 years, and they've been realized in experiments on matter near absolute zero temperature. Our sense in the department that this is just the beginning of a new era. My colleagues in the department and around the world, in both theory and experiment, are pursuing new knowledge rooted in Duncan's pioneering research. This field, broadly condensed matter physics, but also evolving to encompass atomic physics, is vibrant and exciting with discoveries reported at Princeton with remarkable regularity. We all look forward to seeing what this work leads to. There's more great science to come, and we all are just indebted and so thankful for all you've done, Duncan.
Thank you.
I'll give you now our 2016 Nobel laureate, Duncan Haldane.
Thank you.
Yeah, I feel very gratified to have played a part with my co-laureates in coming up with new ways of thinking in condensed matter physics that really have changed since I was a graduate student. There's a completely new focus on quantum mechanics in a way that we didn't understand before. And I would actually also like to say that I was really guided in all this by the tremendous training and mentorship I had from my advisor, Phil Anderson, who really inspired me, even with his undergraduate lectures at Cambridge in my last year that got me so excited about condensed matter physics. In fact, I had two opportunities at Cambridge, one to work with Phil and one to go into string theory, which was about 10 years before its time. Luckily, I chose the right path. And what I say is, that, of course, technically it's kind of difficult to explain what this prize is really for, but what it really is that before we of course knew the equations of quantum mechanics, and we could write down Schrödinger equations and solve model problems, but we really didn't have a proper appreciation of all the kind of things that the quantum mechanics can do. Just knowing the equations doesn't tell you what potential solutions of those equations are. And that's really, I think, the new way of looking at things that's been that I was privileged to contribute to, with David Fowlis also, and Mike Kosterlitz was more on a classical physics, but actually the Kosterlitz-Fowlis ideas were also incredibly influential in the quantum mechanics of low-dimensional systems. So I've worked my way up from starting with zero-dimensional systems with my advisor, Phil Anderson, and my thesis work. Then I somehow worked my way around to one-dimensional systems, chains of atoms or spins, in which I was fortunate to realize that the conventional wisdom about how these things behave, well, actually, while plausible, was in fact completely incorrect when looked at in detail, and no one had really checked the details out beforehand. And this gave rise to some thing which turns out to have been the first of this new class of topological matter, which is a kind of interesting states of matter where the boundaries of this matter is topologically different from regular matter, which means it can't get continuously changed from topological, non-trivial to trivial, and that gives rise to kind of new degrees of, unexpected degrees of freedom on the surface of these materials. And this has been a theme. This, in fact, and then we worked our way up from the one-dimensional case, later to the two-dimensional case, layers of material in a graphene-like structure. And I was fortunate enough to realize again that through actually just working on a toy model problem for some other reasons, that you could achieve what was called the quantum Hall effect without applying huge magnetic fields, which made it a more practical thing. Just you could achieve this just from crystal structures with a particular kind of what we call broken symmetry. And from that little toy model, it went on for a while as a toy model, and later on, the step up to 3 dimensions happened. This happened in Philadelphia nearby here with Charles Kane and Jean Milly, who took 2 copies of a toy model that I found very useful in the 2-dimensional case, a graphene-like model, and stuck them together and found that when you glued mirror images of the thing together, it did something even more interesting, which allowed extensions to 3 dimensions. And all this kind of theoretical work went on, but after that, after it was realized that real materials, crystals that you could find that you could make here in Frick, so such as the Bob Carver is now making all the time, could actually exhibit these topological things, and they had these unusual surface properties that had been sitting in front of people's eyes for 30, 40 years, and no one had noticed it. Suddenly, this became a huge revolution, and it actually fed back the creation of actual materials that behave this way, as fed back. Even my toy model from the late 80s was now made as a consequence of this knowing how to manipulate matter. And the surprising thing about this is, or the implications, I believe, are that there's such a new way of looking at what quantum mechanics can do, and now there's a huge amount of input from what's now called quantum information theory, which is really different ways of looking at old problems, and we're really, topological materials at least have been proposed as one of the routes to the quantum computer, which is the dream, so far the unrealized dream, but that a lot of people are working on. But I can see now that this whole field has burgeoned and has spread as more kind of this new way of thinking has led to new discoveries. And it's quite, whatever the future will bring, I think is a very rich field of quantum engineering, quantum information technology, and condensed matter all coming together. And we've gone a long way from the way physics, condensed matter physics was when I started back in.
Okay, thank you, Duncan. Open questions to the media first, but I'm going to start with one that came in from your hometown, London, from the Evening Standard. Duncan, your day started with a call from Sweden at 4:30 in the morning, but at 11 o'clock this morning, you were in the classroom teaching graduate students, a regularly scheduled class. And Matt Watts from the Evening Standard, a reporter there, wants to know, why was it so important for you to teach class today? And is your teaching just as important as your research?
Well, well, of course. But you know, it's a matter of duty or pride to go back and do one's job. And in fact, I think the lesson should be there. All these are the classes of incoming graduate students, and I think all these graduate students who come in have they have hopes, and I think any one of them could discover something tremendous and new and get a Nobel Prize for that matter, because in fact it's not that you don't get up at the beginning of the day and say, I'm going to discover something great today. You're doing whatever you're doing, and you happen to chance on something through some other route, and you have to have, of course, the insight to see that what you found is something interesting and worth exploring more. But I think most discoveries end up being made for reasons completely unrelated to, they're accidental in some way, right? You were looking at some problem for some other reason, and you found that. So in that sense, so I think one ought to be inspiring. I think it's a good model, a role model, I think, for the students.
Great, thank you. Okay, questions from the media who are here? Any hands that I see? Tell you what. Oh, we've got one, Philip.
So,
could you identify yourself?
I'm Philip Curran from the Princeton Packet local paper. So, does this validate you, or do you feel like you're better at what you now? Does it validate your work and your life's work, and do you get a raise for it as well?
I guess.
Yeah, I expect you will.
Well,
it's one we're happy to give, Philip.
yeah, I think I think my life's work was validated whether or not I got such a prize, and I was very happy that I'd actually been fortunate enough to be able to make such contributions to this field. And I don't think one needs a prize to validate one's work, and one doesn't spend the time worrying about if you're going to get a prize.
Okay. Other questions from the media here? I do have one. Back there.
Oh, I just want to follow up on your question.
Could you identify yourself?
Chiara Nappi, Physics. I just want to follow up on your question. Now we understand why you went to teach at 11 o'clock. I want to know what the student did when you showed up.
Well, they clapped in front of some cameras.
Here's a question from Colin Fernandez. He's a science and environment correspondent for the Daily Mail in the UK. And he wonders, does the award of the Nobel Prize for Physics to three British-born scientists now living in America show that Britain has suffered a brain drain of scientists to the U.S.? He also wants to know how you're going to spend the prize money.
Okay. Well, I'm going to give a lot of it to the IRS.
It wouldn't have happened if I'd stayed in England.
But yeah, the brain drain, when I finished my work, I didn't consciously have my brain drained here, but in some sense, the opportunities were here, and a lot of that time, the exciting work was going on in the States, and I think at that time, there was some kind of policy in Britain. Perhaps, I'm not sure if Mrs. Thatcher was in power then, but there was some attempt by the funding agencies to stress usefulness of work, as opposed to, I guess, the National Science Foundation has always said inspiration-based studies, or studies based on, what do they call it, looking for something interesting. You can't get up in the morning and say, I'm going to discover something extremely useful. Usually, something extremely useful is actually discovered for completely other reasons, and it turns out to be useful. So I think partly there was a kind of, perhaps some kind of politic in Britain at that time.
Great. Okay. If any further questions for the media, or I'll continue to call on you, but why don't we open it up to the broader audience? Who has questions for Duncan, our physics laureate? We have eager mic runners ready to bring a mic to you. Questions? Let me go back to the well from the reporters in Britain. Also, Colin Fernandez from the Daily Mail wanted to know, what applications could your research bring the world?
Okay, well, this is the usual. But at least potentially, one of the things of these interesting states on the edge, especially on these kind of flat graphene-like systems, is that the electrical currents go one way only, in one direction, and in fact one can do this with light. There are analogs of this in photonics, which is the motion of light, and it's a bit like having the difference between a crowd of people moving through each other in opposite directions on a street with no rule of the road. And now this system gives you not just a rule in the of the road where the people going forward are on the left and the people backwards on the right, or whichever way it is in the two countries. But in fact, the two edges are not just divided by a barrier in the middle. They're kind of, it's like two sides of a freeway that are completely split by a long distance. So this allows a better flow of the information without being hindered by sharp turns in the road, which could cause you to bounce backwards onto the wrong side. And at least this has been one of the visions that might come out of such things. But really, I think the main message is that we're going to find all kinds of great things that applying these new quantum mechanical principles to matter will allow us to do, and we don't really know what decide. I mean, the quantum computer is, of course, the holy grail of this field, but whether it happens or not, we'll find out. But there's a lot of money being put into it by people around the world now.
Okay, any other questions from the audience? Yes, sir.
Chris Tully, physics.
Wait for the microphone for just a moment, please.
Sorry. Chris Tully, physics. Duncan, I was wondering what experimental work did you find was particularly compelling for you in the area of topological phases in matter?
Well, I suppose the only real experimental work that motivated me was the discovery by Dan Sui and Horst Sturmer, and who was the other one? Art Gossard, right. Gossard too. They discovered something called the quantum Hall effect, now called the integer quantum Hall effect, was discovered by von Klitzing in 1981, and it was initially a big mystery. It's now has a topological component to it, and quite soon after people had understood it and decided, okay, they understood it completely, this new effect called the fractional quantum Hall effect was discovered by Sturmer, Gossard, and Sui, and that was something that no theorist could understand. So that was a completely out of the blue experimental challenge, and it took a year or two for, I guess, Bob Loftin, who got a Nobel Prize for his discovery, kind of chanced on the right solution, what turns out to be the right explanation. So the experimentalists completely dumbfounded the theorists in 1982-83 with this discovery, and that got us thinking, trying to find ways to explain this. I think in the topological field, in some sense, it's the theorists who've provided the guidance to the experimentalists up till now. So, in fact, they're desperately hoping they will find the fractional equivalent of topological insulators before the experimentalists find it, because we were deeply wounded in our pride that such an unexpected experiment showed up after we decided we understood everything completely.
Further questions? Yes, ma'am. Yes, over here. Microphone's coming your way.
So what projects are you currently working on?
Well,
Or can you not tell?
I'm interested in back to this old problem of the fractional quantum Hall effect, and I've turning my attention a little bit from topology to quantum topology to quantum geometry. And in mathematics, there was a famous Gauss-Bonnet theorem where Gauss made an exceptional, completely remarkable discovery that you could relate topology to geometry. And so I'm trying to go backwards and look at quantum effects in the geometry of these systems.
Yes, back center. Microphone coming from your right.
Hey, Professor Haldane. Are there any yet unconducted experiments you could imagine that might be really helpful if money weren't an object and resources were unlimited?
Well, I don't think the kind of experiments that condensed matter does actually are these kind of experiments that need dramatic amounts of money.
But they help.
They help. We're talking about millions. We're talking about millions.
Good idea. Yeah.
Money on the millions, but not the billion scale. Right? Well, if offhand, I can't tell you which one to do, right? But in fact, I don't. We need there's lots of amazing stuff going on with cold atoms and things, but these are kind of rather small. These are not giant experiments. We don't need to build huge. We do need to have things like synchrotron lasers. We need a lot of facilities for shining various kinds of radiation of the kind that Zahid Hassan does to illuminate these systems with high-intensity light and see how they behave. So we need user facilities, but we don't need kind of giant LHC type stuff. or in fact, there's gravitational radiation needs that. Right?
All right.
I have a more biographical question, Dan. Duncan, could you say something about what attracted you to physics when you were young? Was it something you always felt an interest in, or was there a teacher who made a huge difference to you?
Well, I guess my last but 1 year of school, there was an extremely good chemistry teacher, so I could have gone into chemistry. But the last year was the physics teacher was quite inspiring. And then I didn't know what I would actually at Cambridge. One wasn't, as some other English universities, you're tied down to what you said you wanted to do when you came in. But at least it was sciences. But I didn't have to decide which kind of science. And I found, well, actually, after a few experiences in the chemistry or biology lab, I decided I should not let myself near any kind of nasty chemicals or radioactive materials. So after having a few spills on myself, I decided I was going to be a realist. But actually, I think all these things are probably due to inspirational teachers such as Phil Anderson. And I think the quality of especially higher level lectures is one of the things that really determines what you're going to go into. You have to. So I think the teacher-mentor thing is crucial.
Maybe one or two more questions. Anybody? Hearing and seeing none, this will conclude our news conference. I'd like to thank everyone for coming today, everyone for tuning in from afar, and thanks to all those who made this news conference possible. And I think in about 5 minutes or so, upstairs in the atrium, we will have a reception for Duncan. And we hope to see all of you up there. Please move in an efficient quantum fashion as you go. And let's have one last round of applause.